lot of linear first order circuits. And that means first order in the time dynamics, which usually means that I'm going to have one state variable. Typically, you might think that's either one capacitor or one inductor. You can get a little more complicated what one state variable is in terms of how things are reduced. But just kind of what are sort of a lot of typical forms that you find. And so that's kind of what I want to just talk about here is that you can talk about a couple core circuits, both resistor and capacitor and resistor and inductor circuits. In fact, what happens with resistors when I just replace the capacitor with an inductor? I can also flip the order of these, which kind of makes it interesting too, right? I look at here, I have a capacitor, I have a resistor, I can talk through that behavior, flip the order of the inductor and the resistor. I can also do this with some simple op-amp circuits and do something very similar. I either have a capacitor in one spot or maybe a capacitor sitting connected with the resistance elements. And we could imagine many different permutations of it. But you start to see a pattern happen again and again every time you do this. And so what I'm going to look at here is I'm going to have this for all these values. I'm going to have common values of capacitance R, R1, and R2, as well as inductance. What you're going to find is also there's a set of different time constants that come out of this. And always when you can find the time constant, and it just comes out of the math. It's not like magic, but it usually comes out of the math, and it's usually a way to simplify the math to get something that's in terms of time, which then sort of normalizes your differential equations, normalizes your Laplace transform, normalizes your frequency response. Okay. And if you're really, really fortunate, although you can't do it with resistors, but if you had a case where you could actually change those resistors, change those biases by some biasing, well, then that actually allows you to then to change those values, and that turns out to be a very powerful technique in certain places. So you start off with a time constants. One is just RC, which is also equal to R2C in this case, because those are the same resistor values. Those are 2 milliseconds. R1 and C, which we'll use in one place, is 1 millisecond. And tau 2 is L over R, which is due to the inductor resistance capacity. Remember, time constants for inductances are L over R. It's a ratio that you get from this. And that L over R that you get is going to basically be the L over R, which gives you something, L over R, in this case it's going to be R1, is going to be half a microsecond. Now if it had been L over R1, it would have been 1 microsecond. So that's why when you look at these two capacitive resistor circuits, they're going to be looking at frequencies in kilohertz. When you look at these resistor inductor circuits, these are frequencies that are sort of gauged in megahertz. And these other RC ones are gauged in kilohertz. Just to kind of gives you sort of another visual way of looking at it. But qualitatively, even though when I normalize it, they all feel very similar, because once you kind of center in on what that time constant is, everything looks still very, very similar in terms of the equation. So for this sort of structure, for this resistor capacitor circuit, I get a first order differential equation, which basically gives you a case where it's going to be near 1 and then falls off at higher frequencies. Interesting enough, if the inductor and resistor are this way, I get something that's 1 and falls off. In fact, you could get a better sense. You could write this as the differential equation. You find out you get exactly the same diffie-q's, but different time constants. The other way to look at this in sort of a different sort of time constant is you could have done this in Laplace, and realizing that doing the Laplace version of the circuit, you get over 1 plus s tau, which is what you expect for a low-pass kind of behavior. Interesting enough, these two look very similar, which gives you a case where at high frequencies everything goes through. At low frequencies it gets attenuated and it's decreased, it's smaller, it's a lower level. And it gives you this differential equation where I get the first two terms on the left side equals to a derivative on the right side. Well, this is quite cool. You might imagine, like, wait, I changed the capacitor with the inductor, but basically these two are actually much more similar to each other than these two are, even though it feels like it when I would draw it that way. Both of these give you what is typically considered a high-pass characteristic when you put it together. Now, it's much more fun when you add some op amps into this too, because as soon as you put the op amps into it, lots of things can change and add just in any time you put voltage control, voltage sources, and other kinds of elements into your structure. So, but in this case, what we know is that we have a gain. R2 is twice of R1, so I know the gain is going to be 2. Both cases, I'm going to have that where the gain is 2. And notice that at low frequencies, this is now much bigger than 2, or much bigger than 1. It's now at 2. The gain is actually minus 2. It's actually minus over here, but I'm just looking at magnitude, so you're not going to see the sign here. But notice by putting the capacitor in the feedback loop here, it actually gives me an interesting response where it's high, basically it's 2, and then it falls off. It gives you something that looks exactly like the classic differential equation we had here, except that my input is now minus 2Vn. Everything else looks basically the same. If I look at the lower structure and I actually solve this out, what I would find is, yes, indeed, I get a gain of minus 2 at high frequencies. At low frequencies, it falls off because this capacitance now is in the resistance going into the amplifier, and effectively at low frequencies, this capacitance looks like a bigger and bigger conductance. If I think in Laplace terms, it's 1 over SC, which then in frequency terms means at really low frequencies, this is a gigantic resistance. And remember, gain is this resistance over, well, effectively the series of these two. So as that resistance is huge, that's going to basically make my gain go to nearly 0. And so you can sort of see the different patterns. It's the same pattern again and again and again, but with some slightly different changes in terms of the amplitude values and so forth. Now, as soon as you get into second order, things get much more exciting. But in first order, there's a very clear pattern and patterns that you see all the way throughout.